Industrial path planning for a serial manipulator. Robots are deployed in industries to increase the automation and the quality of manufacturing. They are prone to encounter obstacles or workers while performing tasks. This can lead to risking the safety of the working personnel, colliding with other robots, halting the robot, which leads to increase in downtime and decrease in productivity. Here's an instance of encountering a collision in a real-time industrial setup. The rapidly exploring random tree or RRT is an incremental sampling-based path planning algorithm suitable for complex workspaces like the ones in industrial setups and for preventing collisions. The aim of this research is to understand the parameters of the RRT algorithm, implement the algorithm for continuous paths to analyze the difference between the generated path and the actual path, and implement the algorithm for collision avoidance for different workspace configurations. Understanding the parameters of RRT algorithm. A sample RRT search tree is shown on the right. The RRT parameters are: the start and goal are the Cartesian coordinates of the root node and destination node respectively. The xmin, ymin, and zmin are the Cartesian minimum search limits. The xmax, ymax, and zmax are the Cartesian maximum search limits. The search for goal node occurs between xmin and xmax along x-axis. The same applies for y-axis and z-axis. K is the number of exploration nodes. K number of neighboring nodes are randomly explored, and the node that is closest to the goal is chosen as the next current node. The error threshold is a tolerance between the actual destination and the generated destination. Xrand, Yrand, Zrand are the randomly generated Cartesian coordinates. Note that the path generated is not always optimal. RRT search in a 2D workspace. Here the dimension along z-axis is restricted. The actual path is in blue and the RRT search exploration tree is in red. It can be seen that 6 intermediate points are generated between start and goal using RRT algorithm. The algorithm generates different number of intermediate points every time since the points are randomly generated. RRT search in a 3D workspace. Here the search space is a cuboid limited by the search limits. The search occurs in a three-dimensional space. A 3R spatial serial manipulator was modeled in MATLAB using Robotics toolbox. This manipulator was modeled to have the same kinematic configuration as that of Dobot Magician, which is one of the commonly used desktop serial manipulators. 5 trials were performed. In the first trial, the start is varied, keeping the other parameters constant. It can be seen that the algorithm searches k equals 2000 nodes at a time with an error threshold of 10 mm. The generated path is shown in blue and the RRT exploration tree is shown in red. From figures A to D, the start is brought closer to the goal, but it didn't seem to have any effect on the path. Thus, within the search space, minimizing the actual distance between the start and goal has no effect on the path generated. In the second trial, goal alone is varied. The goal is brought nearer to the start from figures A to D, but it also seemed to have no effect on the path generated like the previous case. Despite the actual distance between the start and goal, higher the space bounded by the search limits, higher the search time, longer the path, and unnecessary is the exploration, as in case D. In the third trial, the search limit along the x-axis is alone varied. For the test shown in figure A, Xmax is 210 mm, which is 10 mm offset to the x-coordinate of the goal. RRT search occurs from x equals 0 mm to x equals 210 mm. This yields an exactly restricted path. In figure B, Xmax is 350, which is exceedingly greater than the x-coordinate of goal. RRT search tree expands in the excess space region, which leads to needless variation in the path. In figure C, Xmax is lesser than the x-coordinate of goal. Therefore, the path is not found in this case. Same results implies for search limits along y and z axis. In the fourth trial, the number of search nodes called k is varied. Higher the value of k, denser the search space, higher the computational cost, more the probability of finding the goal. If k is too small, then a path might not be found at all. In the fifth trial, the error threshold is varied. Error threshold is the distance between the generated goal and the actual goal. It's a measure of path accuracy. In figure A, the error threshold is 2 mm. Path was not found since the accuracy cost was too high. Higher the error threshold, as in figure D, higher the probability of finding a path, less accurate the result. RRT algorithm for continuous paths. In the previous case, paths were generated between two faraway points. A trial of the manipulator executing a path generated between two faraway points using RRT algorithm is shown. In the next scenario, RRT algorithm was used to compute a path between two closely spaced points that are a part of a large continuous path. A serial manipulator was modeled to traverse its end effector along the generated path. Time derivatives of joint displacements were also plotted while the robot maneuvered the generated path. The error difference between the actual path and the generated path is analyzed. For testing the error differences, sample alphabetical paths were considered. RRT algorithm was used to find the intermediate I plus 1th point from the previous ith point. The procedure is shown in the figure. The actual path for alphabet C is executed as an arc in counterclockwise direction using trigonometric functions from 0 radians to 3 pi by 2 radians with an interval of 0.5 radians. Simulation of the manipulator executing C path is shown. The same procedure has been carried out for the alphabet L using linear functions. The L path comprises of two subpaths. The first one is a vertical line from the top to bottom, and the second one is a horizontal line from left to right. Simulation of the manipulator executing L path is shown. The S path was also plotted. It comprises of two arcs. The top arc extends from 0 radians to pi radians in counterclockwise direction. The bottom arc extends from minus pi radians to 0 radians in clockwise direction. Simulation of the manipulator executing S path is shown. Joint displacement, velocity, acceleration are simultaneously plotted for each joint while executing the C path. This has been done for L path too. Here the blue zone represents the joint displacement, velocity, acceleration for the vertical line of the L path, and the green zone represents the same for the horizontal line of the L path. Similarly, for the S path, the blue zone represents the joint displacement, velocity, acceleration for the upper arc of the S path, and the green zone represents the same for the lower arc of the S path. The actual path and the generated paths are shown in blue and red respectively. For C path. For L path. For S path. The original path is shown in blue and the path generated using RRT algorithm between intermediate points is shown in red. The absolute distance between ith point in the actual path and the ith point in the generated path is plotted against I, where I is the position index. A maximum error of 46 mm was observed in the middle of the path for the path C. A maximum error difference of 53 mm was observed at the last point of the locus for the path L. A maximum error difference of 34 mm was observed for the S path. In all these paths, the error distance is small at the beginning because the initial points in the generated path are near to the start. The error threshold for RRT algorithm is 10 mm, which is comparable to the distance between consecutive points in the actual path. This contributes to the error between the actual path and the generated path. Collision avoidance using RRT algorithm. The RRT algorithm was applied for collision avoidance in a 2D workspace. Simulated in Python, Pygame package was used to create a virtual 2D workspace. In order to prevent the complexity of coding the positions of obstacles, the obstacles were sketched in the workspace, which is XY plane, using mouse clicks as trigger events. Here, the user will be able to construct the obstacles, control their positions, size, and distribution. The start, goal, and obstacles are the components of the workspace. 6 different workspace configurations were considered for near zone and far zone. In this context, actual path refers to the shortest path. Configuration 1. Obstacles are constructed to encapsulate the start. In the near zone, despite the goal being nearer to the start, the path is not always straight as the search tree expands around the boundary of the obstacle. The path difference is higher in the near zone than the far zone because the actual distance between the start and the goal is way lesser than the path traversed along the boundary of the obstacles that encapsulates the initial point, which is start. Configuration 2. Obstacles are constructed to encapsulate the goal. Most of the workspace is searched. The search tree doesn't easily narrow down to the goal because the proximity of the goal to any of the currently explored node is cancelled by the positions of the obstacles that confine the goal. So the path difference is greater irrespective of the vicinity of start to the goal. Thus the path differences in near zone and far zone are almost comparable. Configuration 3. When small obstacles are sparsely spreaded in the workspace, the search occurs in an almost free space. The generated path resembles the actual path or the shortest path for the near zone. This is facilitated by the lesser number of obstacles and their sparse distribution. The path difference is very less in the case of near zone, since the actual path is highly comparable to the path generated. In the case of far zone, the search tree expands in the free space, causing huge variations in the generated path, which attributes to higher path difference. Configuration 4. Here, small obstacles are closely spreaded in the workspace. When the start and the goal are near, the RRT search tree encounters fewer obstacles than in the far zone. In the far zone, once the obstacles are contoured, expansion in the remaining free space takes place. Hence, the path distance will be greater in the far zone. Consequently, the path difference is greater in far zone than in the near zone. Configuration 5. Here, a fewer number of large obstacles are present in the workspace. The path difference for near zone is higher as the path generated by the RRT algorithm includes variations contouring around large obstacles even if the goal is not very far from the start. The path difference is lesser in the far zone than in the near zone as a part of the generated path is expended on contouring the obstacles and the rest of the path is expended on an approximate straight path that compensates with the actual path. Configuration 6. Here, a large number of big obstacles are present in the workspace. When the start and goal are near, the path generated is approximately a close fit path generated to expand in the reduced workspace and contour around large obstacles. So, the RRT search tree need not search and expand in the entire workspace. The minimum path difference attributes to the highly narrow search space facilitated by the many large obstacles. For far zone, the entire reduced workspace is being completely explored. Hence, most of the generated path is expended on contouring around large obstacles. Thus, the generated path has more turns and deviations than the actual path in the case of far zone. The table and the plot summarize the path difference between the generated path and the actual path for the discussed workspace configurations. Conclusion. The parameters of RRT algorithm were studied. The algorithm was used between near points in continuous paths. The continuous paths are alphabets C, L, and S. This was done to understand the deviation between the actual path and the path generated by the algorithm. Robot Magician is a commonly used desktop serial manipulator. A robot with the same kinematic configuration as Robot Magician was modeled for its end effector to traverse the generated paths. The time derivatives of the joint displacement were also analyzed for each joint. The algorithm was implemented for collision avoidance and the path differences for different configurations of the workspace were analyzed. Thank you.